Good afternoon and welcome to MAE 106, Discrete Mathematics with Probability. My name is Richard Kohar and this is Lecture 9. Good afternoon to everyone. Hopefully you can hear me okay. Hopefully the connection is decent. Okay. Making sure that the computer is keeping up. And yes, we might be tired. It's the end of the month. But we have some material that we'll get through. So again, we're going to do arguments today. And what this will cover is sections 2.3 and through 2.6 in the textbook. Okay. And what else? Oh, the other thing I should say is there's an announcement. So we'll have test 1. This will be not this Friday, but and I will double check to make sure that I say the right date. Okay. 8th of October, 2021, during lecture period. And assignment 3 has been posted. There is a bit of video lag. All right. We can fix this. Let's see. Okay, so let's see if this will work. All right, so we'll fix that. Okay, so hopefully this fixed that. And so what we'll do is we'll start with the argument. What is an argument? So an argument contains propositions. Okay, and it's these propositions, we break these down or we label them as premises. And the other one is that we conclusion. As for the question about the game, just send me an email about that. Okay, so an argument contains propositions, it contains premises and conclusions. So we'll say that an argument is valid. And actually I will use it as a single. So, and what does that arrow mean? It means if and only if conclusion is true whenever all the premises are true. So we'll do an example. Okay, so what we'll say is that we'll say all Ontarians are Canadian. All Kingstonians are Ontarians. And therefore, all Kingstonians are Canadian. Okay. So I'll draw this line. So pull out some colors here. So these are called the premises. So this is an argument that we've written out. And down here is the conclusion. And in kind of classical logic, they would even call these, this would be like the major premise. The reason for that is it's usually general, and then they would call this the minor premise, and that's a little bit more specific. So this is the major premise. Okay. And so what we will do is we can start to convert this to symbolic logic. So for instance, here we'll say here, we'll call this O. So Ontarians are O. Here is Canadians for C. So rewriting this, we would have O implies C. So there's our premise. We could say here's K. So here's K and O. So K implies O. So this is the premise. And then we can have therefore. Therefore, K implies C. So here, what we've done is we've represented the argument in symbolic logic. Okay, so now that we have this, I'm going to create a truth table. So I'm going to I have three prime propositions. I have O, C, and K. So I'll write that out. O, C, and K. And I'll have the three propositions. O, K implies O. And lastly, K implies C. So I have three prime propositions, so I'll have in total 8. Eight lines. Okay. And now we'll just fill these in. So O implies K. So with this, I stepped in poison ivy and I got a rash. This is true. This is false. True. False. True. 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 And the last one, true. Okay. And just make sure, is that what everyone got while they were filling it out? Does that match? Does that column O imply C the same that everyone got? Sir, that is O implies. Ah, thank you. Perfect. Yes, and I was doing K. Perfect. Thank you. That was correct. So, O implies C. So that's true. This is true. This is false. False. True. True. False. This is also true and true. Okay. So now how does that one look? Good. Excellent. Okay. That's what I got. Excellent. All right. So what we'll do now is we have to do the K to O. So the K implies O. So with this one, we're going to be looking from this column to this column. So true, 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 false, true, false, and the last one is true. Okay, and so everyone got the same thing that I got then? Is everyone okay with this? The K implies O. Yep, okay, good. And lastly, I'll cover up the O here. There we go. So the direction we're going is K to C. So let's do, oops, thought I had a piece of card here for that. There we go. So true implies true is true. False implies true is true. True implies false is false. False implies false is true. True implies true is true. False implies true is true. True implies false is false. And lastly, false implies false is true. Okay? And did everyone get the same thing? Yes, okay. So then the next thing that we need to do is going back to our definition, which was that an argument is valid if and only if the conclusion is true whenever all the premises are true. So the conclusion is true whenever all the premises are true. So what we're doing is we have a test, which is we check the cases where the premises are true, and if the conclusion is also true for all these possible cases, then the argument is called valid. So what we do is we need to look at the premises. Okay? So we're not looking at these prime propositions. Instead, we're going to be looking at these ones right here. And these are the premises. And over here is the conclusion. Right? Because we had done O implies C is the major premise. K implies O is the minor premise. And then the conclusion is K implies C. So what we do is, and I think what I'll do is I'll use a highlighter. So we'll look here is where both the premises are true. So again, whenever all the premises are true. So again, here's a case where it's true, and we look at the conclusion and it is also true. So that's good. We have another case where we have both premises are true and the conclusion is still true. We have false and true, we don't care, don't care. We have another one right here. So this is still true. And don't care. And the last one. There we go. So what we'll do is we'll do our conclusion. So this argument is valid since the conclusion is true whenever all the premises are true. So this is very important. This is that given that we have true premises, if we have a valid argument, it's going to give us a true conclusion. So that's another way of thinking about it. So this is the end of our example. So what we had shown is that this argument, this way of thinking, the way that we've connected these is valid. So another way of thinking about this is that why are valid arguments important? That given you have true premises and you pass them into, let's call this a box here, you pass this into a valid argument, that this valid argument will generate conclusions that are true. One thing to notice, this says nothing about kind of, this is like what I'll call a guarantee. Guarantee. Of course, I can't remember, I can't spell. But it's a mathematical guarantee that whenever you have true premises, you get a true conclusion. But what this says nothing about what happens with false premises. So we've talked about what a valid argument will do, which leads us to the next one, which is a fallacy. And that's an argument that is not valid. You can also think of these as invalid as well. Okay, so let's do a theorem. So let's say that I'll have an argument and we'll say with premises P1, P2, all the way up to Pn, and conclusion, we'll say Q is valid if and only if if I take the premises and I and P2 and ... all the way to Pn implies Q is a tautology. So that's one way of saying this. So put a box around this. It's kind of important. There we go. So again, if you have an argument and it consists of premises, P1 all the way to Pn, and you have a conclusion, Q is valid if and only if you join all these premises together with an and, implies the conclusion Q is logically equivalent to a tautology. So, just as an example, let's say I have this valid argument. I have P and Q. I have not P, therefore Q. This is valid by this theorem if and only if the premises, so here's the two premises together, so I have P and Q and not P. So these are the premises right here. This implies Q. Implies that it's that it's logically equivalent to a tautology. So we can do a truth table for that. So here's number 3. That up here. So okay, so it reconnected. Woo. Okay. And so I have P, I have Q. So I'm just slowly working my way. So I have P and Q. I have not P, and then I'll do those together. So I get the P and Q. And not P. Then I'll do the last one, which is P and Q. Okay, just give it a second. It should come back up. So just create our truth table. So hopefully the connection came back up. Is everything better now? No. Okay. Okay. The other thing is that you might want to check to see if the quality had dropped. Just on the browser, or on the window, just click the little gear, I believe, and then you should be able to see a drop down and see the different types of resolution. And I think the highest quality that we can do at the moment is 1080. So it might have dropped it down. Yes. Oh, excellent. Okay. So those are good tips for next time, just in case the quality dips. That if it's on auto, it'll jump down to a low setting, and then you might have to actually bump it back up again. So let's hopefully, okay. Hopefully that sorts it out. Let me pay really close attention to what I'm doing. So just so that I don't make a mistake. So I'm doing P and Q. So again, just making sure this is it. For it to be true, it has to be both be true, and the rest are then false. I flip the values for P, and then I'm going to do the and on both of these. Thank you. It's good to see that people are helping each other out on the chat. So we'll have false, 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 false. And then I thought I had a little card. There we go. Then we'll take this column and do the implication. So I have false implies true, that's true. False implies false is true. False implies true is true. And false implies false is true. So what we have shown is that the tautology, therefore it is a valid argument. here. So here's section 2.4. This is modus ponens. That's an E. That's the Latin for the way that affirms by affirming. And what this is just kind of an argument. It's a structure of an argument. And it's major premise goes, we start with an implication, so P implies Q. That's what they mean by affirming. So we're going to affirm that this is true. P implies Q. The minor premise, which is to be a little bit more specific, by affirming, it says we get definitely P. So if you're told that there's a cause and effect, you have a cause, therefore Q. That's your effect. Conclusion. So we affirm that P implies Q. We have P. We're affirming P, and then we get Q. So what I can also tell you is that this is a valid argument. So if I did an example, we had done previously like P implies Q. We've been thinking more of like if I stepped in poison ivy, then I get a rash. This says I stepped in poison ivy. So therefore, I got rash. Okay, so what it's saying is definitely that there's a cause and effect. Then you have the cause, therefore the effect shows up. So the theorem is that modus ponens is a valid argument. Or equivalently, we could write that as taking the two premises. So we have P implies Q and P implying the conclusion Q is a tautology. So we can do that either using a truth table. Would you describe this argument as self-evident? No. Sir, shouldn't it not be P for the... So Alex is saying, shouldn't it be not P for the minor premise? No, definitely not. That's a, yeah. No, that's definitely P. Anything else? Okay. Well, this was the end of the example that we had done up here. So that's the end of the example. Because we had done this one up here, right? We were looking at P and Q, and not P implies Q. That is logically equivalent to a tautology. Yep, so I'll just draw a line. We'll just make a little divide here. End of example. And I'll put that little diamond there. That's usually when I say that that's the end of the demonstration, so I'll put that there. No, it's good. It's you should be checking to make sure. I could drop a negative. I could be looking at the wrong column. It's all good that you guys are keeping an eye on this. All right. So let's look at this one. So we could do this, the proof, the first way is by a truth table. So I'll just write out my headers. I just need my lines. So we're going to do P, Q, P implies Q. Then we'll use the and. So then we'll do the P implies Q and P. And then the last one is taking this column. So the P implies Q and P, and doing the implication with the conclusion, which is Q. And this column will be, hopefully, should be a tautology. So all T's down that row. And then that will prove that this is a valid argument. So this is the first way that we can do it. So just filling in our truth table. So this is just kind of our standard P implies Q. Then we'll do, where's my little piece of card? Okay, it seems to have disappeared, so there we go. Cover that up. So I can do the and, so true and true, that's good. False and true, that's false. True and false, that's false. And true and false is false. Right? Did I do this column correctly? Just make sure. Because am I doing the and correctly, or am I doing an or? have at least one that's saying it's correct. Good. All good. Okay, and then I need to cover that up and this up. There we go. So what I need to do, then I'll do this column implies this column. So I get true. False implies false. That's true. False implies true. That's true. And false implies false is true. And again, it's very important in which order we're going, because if we'd gone the opposite direction, we had done like Q implies this premise, we would have got a true, true, and this one would have been false. So we would have come up with the wrong conclusion. So be very careful. This is a tautology. So since it's a tautology, therefore modus ponens is valid. By using so this is the first way that we could do it. We can do it by truth table. And the second way that we could do it is by using the rules of inference. Okay, so I start with the left-hand side. I'm going to show that it is going to be a tautology. Okay, so this is the first one. So the first thing I'll do is I will eliminate this implication here. So I have P implies Q. That's logically equivalent to P or Q and P. And I'll leave this implication. So this is an implication. So I'm just changing, what I'm changing is just this one right here and here. So that's fine. Then what I would like to do is kind of distribute this P. So what I'm going to do is I'm just going to exchange the order. P and not P or Q. So this is when we do kind of changing of the order, it's the commutativity rule. So all I'm doing is I'm just exchanging places. Now, what I'm going to do is I'm going to apply my distributive rule. So I'll take this and apply it to here. The or will switch to an and we'll apply this also to this one, so that I get P and not P. The or, the or I keep. And then we get the P and not Q. There we go. And this is distributive. It's not quite like the De Morgan. The De Morgan would have flipped it, but it, oops. So that stays here. Then the next line that we have, we notice that we have P and not P. And we know that that, what's that? P and not P in the chat. What's that? Okay, so some people are saying it's a tautology, and some are saying it's a contradiction. So just remember, yeah, it's the excluded middle, exactly. So remember, P or not P, that's a tautology, that's the excluded middle. That's the excluded middle rule. And we also had P and not P. So you have something and not something. That's not possible. That's a contradiction. So what that means is that I have, wow, this is not the way I did it. Okay, that's okay. There's lots of ways of doing it. P and not P, so this is a contradiction. What's next? Contradiction or a proposition is just the proposition. And can someone tell me what rule that was, what that we did here by just kind of simplifying or remove, kind of not bothering writing with a identity? Excellent, yes. Okay, then the next one that we can do, could we use domination instead? The domination, no, if there was an and here, you would use the domination, but in this case we have an or, so I'm just going to use the identity. So we have identity. Then the next thing that we can do is I'm going to apply the implication rule. So there's the implication rule again. Oh, and of course I gotta write that down. So there we go. We can't shift these brackets yet, so what I need to do is I'll use my distributive or my De Morgan, right? So I apply the negation to the P, so it's not P. The and switches to an or, and then and not Q. There's my brackets. So this is De Morgan. I can move the brackets because I have the ors, so I can actually move the parentheses around here. Q or not Q. So this is the associativity. We're almost done. Right here. So there is my excluded middle. So there is my tautology right there. And lastly, not P or a tautology is just a tautology. And that is the domination rule. Okay, so that's what we did. By the rules of inference, we started out with the left-hand side. We applied the implication. We exchanged the order of the propositions. That's a good question, Stephanie. If you wanted to be very strict about it, yes. Depending on, because we were following the rules explicitly. So you could do one more step. Or Q or not Q. And that would be your commutativity rule. Okay, so hopefully that answers that question. Perfect. Okay. So that was modus ponens. So again, that's just that we have P implies Q. If there's P, therefore Q. Oops, make sure that I have 1, 2, 3, 4. Here we go. We're on to page 5. So modus tollens. And that is coming from the Latin. And the previous one that we had done was affirming. This one is the denying. So it's the way that denies by denying. So what does these this argument looks like? We start off with that same implication again. So we have P implies Q. So there's the major premise. Then, which is what I think maybe Alex was thinking of, because then the minor premise is not Q, therefore not P, and that's the conclusion. Okay. Okay, so basically modus tollens is just kind of it's very similar to modus ponens. Remember when we said that there was a logical equivalence? So if I had P implies Q, so this is the implication, that we had said that this is logically equivalent to not P implies not Q. Sorry, not Q implies not P. And this is called the contrapositive. Well, if you think of this, by modus ponens, which is what we had done previously, is that we had the implication. So just going back to what we had originally. So there is our implication. There's our implication. Then they said the minor premise would be affirming kind of the cause. So that's the not Q. Implies, sorry. And then the conclusion then would be the effect. So this case, Q is Q. Here would be not P. So what I'm trying to say here is that this would be by modus ponens. And right here, you can rewrite this line, the not Q implies not P, to be P implies Q. And this is modus tollens. Okay, so you see the similarity. Right, because these two lines are logically equivalent. So here we go. So just returning to our poison ivy example. So here's my P implies Q. If I stepped in poison ivy, then I get a rash. Here's the not Q. I didn't get a rash. Therefore, so I didn't get a rash. Therefore, I didn't step in poison ivy. So there's an example of modus tollens. So just comparing that to what we had done in modus ponens. Again, if I had stepped in poison ivy, then I get a rash. I stepped in it, I get a rash. And what it's kind of thinking about is it tells you the cause and effect. I don't have the effect, therefore I don't have the cause. Okay. I should also say that this is also a valid argument. So again, modus tollens is a valid argument. Or in other words, what we can say that the premises, we have P implies Q and not Q, implying the conclusion not P is logically equivalent to a tautology. So again, proof. You can do it by a truth table, try this yourself. It's very similar to what we had done previously. So like this, set it up, and you can find that you should be getting all truths. Or the second way, which is by rules of inference. Does that say theorem? Yes. Good. Okay, so just making sure I have 4. Yeah. So just kind of, we had shown that modus ponens was a valid argument. Same thing, there's modus tollens, and we can do this by rules of inference. On the test, do we get an option to do either the truth table or rules of inference on these types of questions? You will on the test, you'll be asked specifically for one way of solving it. So yes, exactly, the questions will specify. So that's a good question. I'll put that here. Question. Do we get a choice between rules of inference? The answer depends on the question. It may specify one specific method. Not all the time, but it may. And if it does, you have to follow that instruction. Otherwise, no points. No points. And we want points. So, rules of inference. Modus tollens, right? So on the left-hand side, we started out with the implication P implies Q. That's the first major premise. And the second premise is not Q. Okay. And then we're going to imply the conclusion, which is not P. Okay, so this is logically equivalent to, which one are we going to do first? We'll get rid of this implication first. So this one. So I'll treat this as one big proposition. So I have not all this stuff inside here. So not, so not, and then I have a bracket. P implies Q and not Q. That's now an or, not P. Right? So it's, again, to do the implication, it's the first proposition implies the second proposition is logically equivalent to not the first or the second. So there's not the first or the second. Here's the implication. Okay. Then what I'm going to do is kind of like the reverse of the De Morgan law, right? So with De Morgan, I have not P or not Q. That's logically equivalent to P and Q. So same idea here. I have a not and a not here, and then there's my or. So I'm going to bring the negation out. So this proposition here is going to be inside here. So I have P implies Q and not P. But there's two implications. Yes. I'm not going to get rid of them yet. Yep, I see that there is two implications, but don't worry. Okay. And P. Good. So this is by De Morgan. Okay. Now I'm going to shift these brackets because I have an and right there. So I'm going to move this bracket here and this bracket here. This is by associativity. Okay. I'm going to just change this order here. P and not Q. This is the commutativity. So all I've done is just exchanged the order. Okay. And I'm kind of getting tired of carrying all this. So what I'm going to do is just here's an aside. Okay. So over here, I'm just going to say I have P and not Q. Okay. What I'm going to do is, what I'm going to try to do is convert this to some sort of implication. So P implies Q or some form of that. That's what I'm trying to do. So I'll not P and not Q. So that's the double negative. Then I can do a De Morgan, right? So same idea. I will pull out. Do we get to use a formula sheet? I have to check on that. Okay, so doing the De Morgan, I can pull out a negative so that I'm left with not P or Q. This is De Morgan. In either case, it's best to be working these rules, and they almost, you remember them by practicing them. The next one that we're going to do is I have a P implies, well, not P or Q. So that is logically equivalent to P implies Q by the implication rule. So I'll write that over here. I got not P implies Q. Okay. So you can almost see what's going to happen next. I have a I have a proposition and not a proposition. So if you think of this as like R, and here's R, so this is R and not R. That's a contradiction, which means that this would be always false. And then I have the negation, which then converts this to always true. But we don't have a rule like that yet. So what we'll do is we'll distribute this negation. So I get not P or Q. Applying this negation to this proposition, this switches to an or, and we get a double negation here. You should know them. You should be thinking that it's, yeah, I would be trying to commit these to memory. And then lastly, so this is De Morgan. Yes, we did a De Morgan. And then lastly, we have not P or P, well, not R, or you can think of it like that. But you just treat that as like a proposition. And so that is a tautology. That's by the excluded middle. This is the double negation. And we're done. So there's the proof for modus tollens. Okay. And then we have syllogisms. And these are kind of just special arguments, very similar. We've been looking at arguments that have like 3 propositions. So this is an argument with 3 propositions. So 2 premise, and then 1 conclusion. This one's called the hypothetical syllogism. Okay, so the way I usually think of it is it's by connection. So it's like usually P implies Q, Q implies R, therefore Q implies R. It forms like a chain. So I will actually write that out. So the major premise is the P implies Q. The minor premise would be Q implies R. And then, therefore, P implies R. So this is the conclusion. Why it's called hypothetical is because, unlike modus tollens or modus ponens, when we look at modus ponens, we have the implication or the hypothetical, and then we actually specify one of the premises, like one of the one of the causes and then the effect. So one of it does show up. So there's kind of our hypothetical. We have it show up, therefore there's the effect. But in this case, they call it the hypothetical because we never assert that one of these prime propositions. These are just implications. So we're implying, therefore we have another implication. So what I can show you is, let's do an example. Let's see, how do I spell Socrates? Socrates. Socrates. So this has been known since the ancient times. They said Socrates is a man. So we'll say that this is P implies Q. So this is Socrates, this is P. It's a man. All men are mortal. So here we have is a Q. Here is the R, and then we can finish this off with, therefore, Socrates, so we have P implies R, which means that Socrates is mortal. Again, you can think of it as a link. You can also come up maybe with like a sort of a picture. So kind of an idea would be like using some circles. So we could say that here, this is Socrates. Socrates is a man. So again, he's inside the kind of circle of a man. And then all men are mortal. So that means that the circle Q has to be inside R. And so we also see then that P is also inside of R. So Socrates is mortal. So this is theorem. The hypothetical syllogism is valid. And for this one, we can do, we'll do a proof by truth table. have room. So new line. So we have three prime propositions, P, Q, and R. We have P implies Q. We have Q implies R. And then the conclusion is P implies R. So again, don't forget, we're going to be looking at these. These are the premises. And here's the conclusion. And we'll use the definition of a valid argument. So 2 to the 3 is 8. So it means I'm going to have 8 lines. And we just do the implication rule here. So make sure I look at the right columns, right? Or the correct columns. Okay. Now we'll look at Q implies R. So that's this column implies this column. So true, false. And the other question you should ask is, will you be expected to have memorized all the truth tables for each of those connectives? And the answer is yes. Okay, so now that we have the truth table, I should take a moment and does everyone agree with what I've written? Did I make a mistake? Hopefully I didn't. If I took my time, I was paying attention, I was picking the right columns and applying the right operator. Okay, good. So then we don't look at these ones right there. We're just looking at the premises and the conclusion. And so again, excellent. Oh, someone's buffering. Okay, hopefully it comes back. Seems to be okay on my end. So again, going back to our original definition, it's valid if and only if the conclusion is true whenever all the premises are true. Okay. I thought the emoji was, yeah, I thought I had it interpreted correctly, but yes, thumbs up is good too. So we're looking for when the premises are true, that the conclusion is also true. So this is good. I don't care about this. I'm looking for when I have true premises. So here's another case, and the conclusion is true. So okay. So then the conclusion that I would say is that since the conclusion is true whenever all the premises are true, therefore the hypothetical syllogism or syllogism is a valid argument. Okay. And we have time for one more. So we have two syllogisms. There's the hypothetical, and then there's also something called the disjunctive syllogism. So this one doesn't have the hypotheticals. It doesn't have the implications. Instead, this one's going to have, in the major premise, it's going to have a disjunctive statement. So I'll make sure I'll finish off my proof there. So the last one is the disjunctive. So the disjunctive, like I said, it's got to be a disjunctive statement. So we're going to have P or Q. So there's kind of the major premise. The minor premise, again, something that's a little bit more specific. This time it says it's not P. Okay, so it's definitely not P. Therefore, what can we conclude? Well, we assume that this has to be true, so it's either P or Q. We're told it's not P, so that means that, so if we're thinking over here, kind of our thought bubble here, we have P or Q, and we were told that it's not P. So this has to be false. Which means then for this to remain true, because it has to be for this to be true, that we need to have the Q be true. So therefore our conclusion is Q. Right? If it's one or the other, and we've eliminated one of the choices, it has to be the remaining choice. Again, this is to ensure that it's a valid argument. Right? Because a valid argument has only true conclusions whenever the premises are true. All the premises. You can almost think of this one as kind of like an elimination one. Poor old Socrates. We're going to use him again. Socrates. We're going to say is either alive or dead. Okay, so we'll say that this is P or Q. What would it, oh sorry, I didn't look up. Someone wrote, what would it imply if it was from left to right, true, true, false? That's a good question. I will get back to that question right after I finish this. Socrates is not alive. So there's my not P. Therefore, Socrates is dead. So again, you can show that this is true by a truth table. Somebody was asking me, let's say we'd gone through this. The question is what would it imply if it was from left to right? True, true, false. So he is asking about this one right here. Okay. So what this would say is if we got to the end here, we had one of these where it was true and true. These are the premises. And the conclusion was false. Then it fails. It is not a valid argument. Since the conclusion is not true whenever all the premises are true. In this case, it would be called therefore it would be called a fallacy. Okay, but that's a good question. In the next lecture, we will see examples or explicit of invalid arguments fallacies. Yes, I will have office hours before the test. And what I'll do is, again, if you are so inclined, now that we've gone through this, just as a review, you should take 10 minutes tonight and do this one. We have our disjunctive statement, the P or Q, and not P. implies Q is a tautology. I don't think I have heard of Logically Fallacious. I will have to look up that book. Yes, there are lots of examples of very logic being passed, bad logic being passed off as good. And yes, it's a lot of fun. And it's can be a bit like an exercise. Definitely check out some books like that. But yes, I'll check out that book for sure. And while people, since I have about a minute left, since people are, if you have any more questions, feel free to leave them in the chat. I'll probably have an office hour tomorrow via Zoom, so just check for that link tomorrow after the lecture. And again, if there's any more questions, you have an assignment to work through. And what I'll do is I'll just kind of leave this little tidbit right here, just in case. If you are planning to work on this as an exercise, don't look at this then, and you can come back to it when you've done it, and you can have a look at it. Okay, so in this case, I'm just implying the implication. Then I will just distribute this to each of these. That switches. So again, that switches from an and to an or. Get not P. So that's De Morgan. You have a double negation right here, so you can drop that. Again, any other questions before we sign off? What am I doing next? I'm going to shove these brackets over because I have here and here. So what that means is that bloop, and over here, there we go. So I have the not P or Q, or I'll have the bracket P or Q. I have a negation. I have a negation here, so you can think of that as not P or P, and that is a tautology by the dumb excluded middle. And by shoving these brackets, that's the associativity. Okay, an hour and 50 minutes. We're done. I'll see you all tomorrow. Thank you for tuning in, and thank you for participating in the chat. It's always good to see everyone, and have a good night. Take care.